All right, let's talk about stacks, queues, and linked lists today. Right, so both are all the three are kind of like a fundamental data structures and used a lot. And in very specific places, they will make life very easy as well. So let's go quickly definition one by one of each of these. So first of all, what is a stack? Let me talk about it. Let's begin with stack. It's a very simple data structure. So any data structure, any type that gives us this facility of remembering the past action in reverse chronological order would be a stack. So if I, let's say, perform some task T1, then task T2, then task T3, whatever. And then if I want to retrace my step back, then retracing back, if any structure can provide me this back, that I was doing T3 and then I was doing T2 and then I was doing T1, then that would be a stack. Very simply, people have different ways of generalizing this. Suppose you have a stack of plates, right? So suppose you have a dish, and then you put another dish on top, then you put another dish on top, and you put another dish on top. And when you are taking the dishes out, the dish that went last comes out first, and the dish that went first comes out last. So that's basically consider a stack of book or a stack of dishes or whatever you want. So, but that is the idea. Whatever goes in last comes out first, and whatever goes first comes out last. And in real life, it's applicable pretty much everywhere. For example, browsers. Simple example. All the browsers have this back button. So you go to site 1, then you go to site 2, then site 3, site 4, and then you start hitting this back button. And you go back in the order you came. So that basically uh, is implemented, some form of stack is being implemented there. In programming also, we are all familiar with, for example, how functions are called. So just give me a second. Yeah, no, it's good. Come on, and just even in programming, for example, suppose you have some function 1, right? And then function 1 does some work. Then it calls function 2. Then it resumes its work. And then basically it might be calling function 3 here. And then it ends. Then you have some function 2 somewhere sitting, and then function 2 is doing some work. And it might be calling, let's say, len of something. And then function 5. And then it finishes. So how do programs actually remember this? So for example, the program counter enters here. The program control, enters here. The first line is executed. Then the line number 2 is executed. Then line number 3 comes. At this point, a call to this function has to be made. And all of these rest of the lines are going to be executed after this, right? So the call can be made, but then once this is done, how do we know where to come back? What programming languages do is basically they create a function stack. So they first create a stack and they put this point, return point here. Suppose this was x equals to f2 or simply f2, doesn't matter. So now we know. So what gets put here is that f1 is on stack. F1 is on stack, and maybe some line. I'm just abstractly writing. Okay, no, it probably is not line, and it should not be line. So line 100, and then you go to on to function 2. Then function 2 is being called right now. Then this line number 1 gets executed, line number 2 gets executed, line number 3 gets executed, and then come to len. Now our program control has to go to len function. So it puts function 2 on stack, and maybe something, let's say line whatever 25, and then len function is being evaluated. Since len function is not calling anything else, we assume for the sake of this argument right now that len is not calling anything else, hence len gets executed. So once len is run, okay, the program has processed len function. Now it needs to go back. So where should it go back? It checks the stack top. What is at the top of the stack? And that item is removed from the stack, and it tells us that, okay, you have to resume from here. So you resume from here. Or supposedly this was x equals to this len. So this len gets evaluated, and then stack is popped to find out that the value of this len has to be given to this guy. And then you continue forward. Then you implement F5 similarly. But eventually at some point of time, F2 is done. Just give me a second. Eventually at some point of time, this is done. Once this control reaches here, then you need to find out where you are. You look at the stack top, which is F1, and then you remove this item, and then you go to this point and you resume your work. Point being, stacks are used everywhere in this way. To preserve the reverse chronological order of events, stacks are important. And this is why, for example, if something happens here, there is a problem in your code here, and your program crashes, then what you print is a stack trace. Stack trace, basically, if you notice the stack trace, it goes from the most specific error down to the general error. So it goes in that way. It starts it will say that the problem occurred on this line n, in function 2. And then it will go back and tell you that in function 1 on this particular line, the problem occurred. And then whoever was calling function 1 will program control will report that. So that's how you get the stack trace as well in programs. But that's the idea of stacks. Stacks are very useful in certain situations. Now, let's look at the operations that we refer to in stacks. Suppose this is a stack. Stack, when you want to put an item into the stack, that item is called push. I think all of you are pretty familiar with all of this. I'm just revising these concepts. You put the stack, push the item in the stack. And when you want to remove an item from the stack, you pop. So the only condition here is that items can be added and removed only from one end of the stack. Right? There is no way to remove from the other side. And in terms of implementation, actually there's one more operation. Sometimes you want to look at what the top of the stack is. So people call it stack top or peak function. Well, that tells you what is present at that particular, we just want to, let's say, whatever, look. Then this is peak function. You can implement, now let's come to implementation. You can implement the stack using an array or a linked list. Linked list we have not talked about, but You can implement it using a linked list, and possibly other combinations of stuff. You can possibly do that. But the most common one implementation is the array one. So in an array implementation, what happens is you create an array. Or a Python list. And indexes are there. So zero index represents the bottom of the stack. That is, items cannot be inserted. So insertion and removal is not permitted. You can only do append. So basically you can keep adding item from the back, and then you can do a pop, which is removing the item from the back. Those are the two things you can do. Since, I mean, if you're using C++, STL, or Java, or basically Python, you don't have to worry about the array size. Array can be expanded on demand now. Earlier, when I used to code in my university assignments for the stacks, we had to take care of this thing that stack would be of size n. So we would create an array of size n in C++, and then we'll have to check. So that means that there are only n minus 1 items. And then we'd have to check whether the stack size is expired, so we cannot push anymore, or we cannot do certain operations anymore. But with I mean, if you right now, you don't have to worry about it. You use Python list, you just keep adding items to the stack. It will automatically, size will be increased endlessly. So you don't have that constraint of space here in that way. So basically, that's how you can implement a stack. And implementing a stack is actually not a very big deal. It's a very small piece of code, and I can send you that code. I can actually code it after as well. So it's actually really straightforward. In the Python class, we actually do that. In the classes section, we code a stack and queue and all that. But yeah, this is not a very complicated piece of code. So in this case, suppose that I'm implementing a stack using Python list. And I can do 3 operations: push, pop, and peek. Then what do you guys think will be the complexity for these operations? Like push operation, for example.
N.
Why do we think it's n?
Like if we have an element to push in the stack, so the operation will be N.
I mean, in that way, yes. But I'm asking, let's say you have a stack, a running stack with some items in it. Okay. 5, 9, 4. And then you want to push another item, let's say 100 in it. What is the time complexity of this push operation?
1, because we are pushing one item.
Right. So pushing is O1. That is, you just add item to the back of the list. Right. That's an average time of O1. What about the pop?
The same one.
What about the peak?
Peak we need to search.
No, peak is just the stack top. Whatever
Okay.
is at the top, you just return. So if you have a stack, let's say some array of -1 is all that you need to do to get the last item. That's it. So that is the fundamental theory of stack. The term that people use for stack is last in, first out. That's the acronym LIFO, last in, first out. Very simple use cases for stack. Okay, if you think about it, Very simple use cases for stack are, suppose you have a string, um, and you need to reverse that string. Okay, you need to reverse that. One of the things that you can do is you can create a stack, and then you can start pushing the items, all the items of the string here in the stack. So you will have S, then A, then T, then U, then R, and then N. So once the string is exhausted, you have this stack, and then you create another, let's say string, whatever result, and then you start popping items. So you get N, R, U, T, A, S. Very simple example that works here. If you check lead code, there are several problems on stack based off of actually a classical problem in stack, which is called uh, balanced parentheses, right? So some of the classical stuff in stack is basically, first of all, what do you call postfix notation. How do you write postfix notation? And then, well, like parentheses. What are these problems? Actually, I'll just explain one. For example, suppose you have an expression of some sort. Suppose x equals to a plus b plus c. The question is that syntax a valid syntax? And the answer, so in this problem, we are not concerned about this a at the moment, or this b or c or plus at the moment. We are concerned about the parentheses. These parentheses are okay. If it was something like, let's say, a plus b, then this is not a valid expression because this parentheses does not have a closing parentheses. So how do we actually determine whether a particular expression is balanced expression or not? We can, so that problem is a classical problem in stack. What we can do, what we can do is we can talk about it in the next session maybe, or something. You guys can try it out, and then we can talk about the algorithm for solving that. Opposed to the stack is another structure, queue. Queue is again a fundamental data structure. Fundamental in the sense that it's used, is basically in the beginning of data structures, we learn these data structures and they're used everywhere. What queue does is, queue is exactly like a queue. So suppose whatever, let's say the queue is exactly like, for example, there is let's say, and whatever ice cream station here, and kids are lining up. So first kid comes, and then second kid comes, and then third kid comes. Basically, as people come, they come from the back of the queue, from one end of the queue. Okay, and who gets the ice cream first is person who came first. So this guy is the first, and this guy is the last here at the moment. So opposed to stack, if you notice, the entry from here, the entry and exit is not from the same place. The person who exits is the person who came first in this situation. So this guy will exit first. So just like stack was last in, first out, a queue essentially is a first in, first out. So whatever comes first is, whatever item comes first is processed first in that way. So this operation of joining a queue is called enqueue, and this operation of coming out of a queue is called dequeue. Just give me a second. Yeah. So that is a queue. Once again, queue are very useful in real life. What kind of problems do get solved with queue? For example, scheduling problems. All type of scheduling problems can be solved with queue, right? Suppose you have processes like, for example, your computer. It has some processes P1, P2, P3, and all that waiting to be processed. Like your computer can only process certain things at a time. In the most simplistic model, if you understand your computer to be one CPU, one core, one threaded, then essentially how things work is that a queue of these processes are created. So what happens is, just give me a second. Something in chat. Basically, you have a queue of these processes gets created. So basically, suppose P1 came first. So P1 is at the front of the queue. Then P2 comes. Then P3 comes. So all of these uh, processes are waiting. Now, as soon as the CPU cycle is available, P1 is taken and P1 is processed to whatever extent can be processed. And then P1, after the processing is done, is put back to the front of the queue, to the back of the queue. So now we have the number for P2. Whenever the next CPU cycle comes, P2 will be processed in this way. So in this way, whenever you want to preserve the order of processing, like who came first and how you want to process, you will use queues in that situation. So that's the example of queue. In data structure itself, queue will solve a lot of our problems in graphs and trees. For example, the BFS algorithm is an ideal example of using a queue. If you notice that algorithm for a second, so suppose you have a tree. Okay, if you have a tree, let's say this item is A, then this is B, C, and then D, E, F. Suppose it's something like this. So I'm writing a tree, but I'm showing you BFS. So basically what will BFS would be is that you will print this item and then all its neighbors first. Then you will process its neighbors first. Then you will process the neighbor of B first. So it's DE. Then you will process the neighbor of F, C, which is F. How do you achieve that? Is by creating a queue. Uh, and this is a good example in that way. So suppose what you do is you create a queue and you start adding items to the queue. So first you say, I'm processing A. So A is in the queue. And then you process A. By processing, I mean you do something with A, and then you put the items children of A inside the queue. So first you put B, so B gets here, and then C gets here in the queue. Then once you process A is moved out of the queue and it's gone. So you can just delete it. Let me just delete it. Then comes the processing of B. So when you process B, what you do is you take the B out first. So B comes out, and then you do some processing with V, whatever you want to do. And then you need to make sure that after this whole level is processed, the first thing to be processed is the children of B. So you push, NQ, the children of B in here. So you'll D and E like that. And then B, after the B processing is done, you remove this. Now, what is at the top of the queue? So we DQ that C. So C comes out, we process C, and then we NQ the children of C in the same way. But that's how you can preserve the order. That's how you can tell a computer to know who is ahead in the line after this whole processing is done. So computer can process it. So now you can just process whatever. C moves out, and then you can just do D and then E and then F like that. So this is very useful in graph algorithms where you are doing BFS. But apart from that, it's useful in a lot of places. Let's say somebody is asking you to design a scheduling algorithm which is least recently used, like implement a cache, least recently used cache. Queues come handy in all of these situations. But we'll talk about this later. I'm just want to give you a brief idea of all of these things first. Now, implementation of queue. A queue can be implemented using various data structures. In fact, there is a uh, actually, yeah, that's fine. Um, one of the natural choice is arrays, for example. Another choice is linked list. This we will talk about after we are done talking linked list. But let's just look at the very basic implementation in terms of array. So you can once again use a Python list. So suppose you have a list. And in this list, you can make a decision of which end, let's say this is the zero index, which end to use for NQ and which end to use for DQ. You can make that decision. Suppose I choose that I'm going to use this for NQing. And this I'm going to use for DQing. So now, whatever this is, the operations are slightly different now. So if I need to NQ, let's say an item, so let's say when I have to NQ the first item, it's very simple. Suppose I have these items 5, 9, and 2. So the first item is very simple. You can just put it at the item 0 when you are NQing. But now when you need to NQ 9, then remember what arrays are. Arrays are contiguous blocks of memory, right? They are fixed in the spot. So if you need to put now 9 here, you need to move 5 here. And that's how 9 comes in this location. Now, if you need to put 2 here, then essentially you need to move 5 over to here. So 5 comes here, 9 comes here, and 2 comes here. In DQ, all you have to do is just pop whatever whatever you want to pop. So that's whatever the last item is, it gets popped. So that's NQ. Similarly, if you decided the other way, for example, if you were deciding the other way, that is, you're going to NQ from here and DQ from here. Then NQing would be just an append operation. In this case, it will just be an append operation. You can just keep adding items from the back. So 5 comes first, and then array size increases, and you become 9 comes, and then 2 comes, and essentially you have something like 5, 9, 2 in the end. So NQ is rather simple. But when you DQ, as soon as you remove this item out, then essentially what you have to do is now shuffle everything. So 9 comes here, 2 comes here. So essentially 9 moves to this location and 2 moves to this location. So it becomes 9 and 2 once 5 comes out. So if you use arrays, one of the operation will require shuffling of the list in this way. And just give me a second. Yeah. So one of the items will require shuffling of array in this way. So if we take the first implementation, suppose I take this first implementation as the implementation, okay? Then the operations here are enqueue and dequeue. Who can tell me if I want to, if there is a queue, existing queue of size n, okay, there's a queue of size n, and I want to, if I want to enqueue a new item, what would be the time complexity for that?
If it's a array list, then it will be n
Why would it be n?
because we need to shift the elements.
Exactly. So that enqueue becomes O of n. And what is the dequeue? What is the dequeue time complexity?
And
O
D,
one.
Why O of 1?
It's just one element that we are dequeuing, right? So
Exactly.
yeah,
Yeah. We just need to do a pop in that
yeah.
case, and whatever append or, oh, sorry, yeah, pop. And in the other list, if we choose the other implementation, then dequeue would be, enqueue would be O of 1 and dequeue would be O of n, essentially. So that's a queue. Once again, you can implement it using an array and Python list. What I'll probably do is I'll send a video of my Python class where I do this. It's not at all very complicated. It's pretty simple. The last structure I want to talk about, because this factor is also remaining, we need to talk about this guy as well here. An implementation of queue using linked list is the linked list. Why would you use linked list? And what, first of all, what linked lists are, and why would you use linked list? In what situation are they helpful? So what is a linked list? First of all, a linked list, unlike array, which is a contiguous block of memory. So if I say whatever int array equals to new whatever uh, something 5, then 5 items are allocated in the memory. Linked lists don't work that way. In linked list, we create individual item nodes. So if I want to store, let's say, number 5, then I create a block of memory and I put a value 5 in it, somewhere in the memory. And then if I want to store 9 after 5, then I create another block of memory somewhere. And in order to mention whether what comes after, we have another data type in this to point to this 9. So this thing, which contains the data item and this information about the next item, is called a node. So a node contains a value and a next to find out who is next after this. So if I do something like node.next, I can get to the next item in the queue here. So once again, unlike array, what we do is in a linked list, we create a node with a value and we put it somewhere in the memory. Now assume there is a linked list I want to create, something like, suppose the first item is 5, next item is 9, then you have 14, then you have 7. So this is these are memory areas. So this can be, let's say, M1, this can be M2. And let's say you want to create another item, then it might be somewhere here, 14. And this tells you that this item is here. And then next item is 7, which might be, let's say, here. This is 7 here. And at 7, let's say 7 is the last item, then what you can do is that this guy, the next guy for the 7 can be none. Or I'm going to use a symbol of, let's say, grounding that I read in a book, which I like. So that means this is the end. The question is, how do we find the first? We keep track of where the list starts with the head element. Head element always points to the first item in the list. So generally in a linked list, we only have reference to the very first item inside the linked list. And then if we want to get to the next item, then what we do is we do head.next. Something like whatever the next item is. Let's say I want to call it current. I say current equals to head.next. So that will take the current to this place, location. And now if I do current equals to current.next, I'll be taken to this item here, 14. And in the similar way, I can continue till my current is not equals to none. At some point, I will come here, current will be here. And then I will say current equals to current of next. That will make current equals to none, essentially. And in the next iteration, I will lose that value. So that's the how you loop inside. That's how you traverse the item inside the linked list. You start with a current which is equals to head, and then you keep iterating to current.next till the current is none. That's how you store items in a linked list. Any questions, first of all, in this? All right. So usually linked lists are implemented in the form of classes. Of course, stacks and queues are also implemented in the form of classes, but here you have two different classes. So usually what you do is you create a node type of a class, which represents a node object. What node has is essentially two values, value and the next item. Then when you create a linked list, you insert the item inside the node. For whatever item you want to insert, you create a new node. For example, you want a new node, you say temp equals to node to invoke this node, and then you put whatever temp dot value equals to whatever value you want, xyz, and temp dot next equals to whatever value you want to invoke, whatever value you want to put. So that's how you do with the linked list. Now, fundamentally, they are different, right? This is very different from array. In an array, all the items are together in one place. So an array is all the items are in one place. So suppose you're adding items inside the array and array size exhausts at some point of time. Then what the implementation is done in Python or let's say in Java is a new array is created of double the size of the initial one. and all of these items are copied. And then you can continue adding more items. Once this exhausts, a double the size of this array gets created in the memory, and then you push all the items of the current one to that one, and you delete the old one. Linked lists don't have this problem because linked lists essentially create only one node at a time, and this node can be anywhere in the memory. If for array to initialize, you need contiguous block of this memory. For linked list, this can be anywhere. So you have node 1 here, you have node 2 sitting here, then you might have node 3 sitting here. It is going like this, and then you may have like node 4 sitting here. So, and you allocate the space as you need it instead of like an array in which the space gets doubled. In the linked list, you create the space as you need it. So this way, linked lists tend to be more space efficient. They tend to be more efficient, especially in the case where you have a lot of data, and a lot of data is being added and removed dynamically from that list. Let me give an example. Once again, let's compare these two different things. Suppose you have arrays again, and you have linked lists again. So you have an array of, let's say, some sort, and then you have this 5, 9, 2, 7, 8. Let's say you want to delete this 2. Okay, you want to get rid of this 2. What does that mean? That means that you need to shuffle the entire array here like this. Compare this to a linked list. Suppose you have the similar items in linked list. You have 5, you have 9, you have 2, and then 7, and then 8. And what you need to get rid of this, they are like this, for example. And suppose you need to get rid of this 2. If you need to get rid of this 2, then essentially all you need to do in a language like Python is that this next item, instead of pointing to 2, whatever is the previous item is, let's call this previous. Let's say this is the item that we want to delete, current, previous. So previous dot next is at the moment pointing to current. We need to change this and point to current dot next. So this link, so I mean, you can keep this link active, I don't care. But all you need to do is just move this guy to this guy. And this 2 is out of the linked list now. And then you can get rid of this as well, up to you. If nobody is referencing this 2, then it will be marked for garbage collection and it will be taken out by the garbage collection engine. But essentially, all you have to do is switch one pointer or one reference to the one node, skipping that existing node. And you get rid of this 2 completely from here. So this way, if you notice, these deletions and insertions in the middle become very easy. In a similar example, if you think about it, if you were to insert something, if I was to insert, let's say 5 here, let's say 20 here, then all of these need to move in this direction to create a space for 20. But if I need to insert 20 here, I just create a node 20, and then I just rearrange my links. 9 points to this guy, and this guy points to this guy. And you have essentially changed the list with just 2 operations every single time. 3 operations, sorry. That is, you create a node, operation number 1, then you shift the previous reference, and then you shift the reference from this current node to the next one. In 3 operations, you will always be able to add a new item, regardless of how big the list is. So all this shuffling is prevented. Any questions?
So deleting an item from an array is at order of n. If I have to remove this 2, I can just point it as array of 2, like, and then I can delete, right? So, but still it's an order of n because internally it has to reshuffle and bring someone to the second position.
That is correct.
Okay.
Even the insertion is in that way. See, if it's not an append, but an insert, then insert is O of n. Append is
Got it.
O of 1 because it's just the last item, you just take it out.
Right. Okay.
Now, there is a catch here. And the catch here is that although these items, for example, insertion and deletion in a linked list is constant time. All right. Just give me a second. Even this is a constant time, there is one problem of finding the node that where you want to do this operation. Because in a linked list, you have this head pointer, head reference. And let's say I give you a question that you have to add an item after 2, and the value of that item has to be 20. Then in order to do that, or suppose I ask you a simple question, not after the item, I say in the third place, or in, let's say, 1000th place, add an item called 20, an item with the value 20. So in order to reach the third place or the 1000th place, you have to start at the beginning, and then you have to do next references till you count till whatever that k or 3 is. If I was to ask you a similar question in the array, that on the third item you do this, then it is an O1 operation. Finding an nth item in an array is O1 operation, whereas finding an nth item in a linked list is O of n operation. So which comes to finding, let's say, index operation. So that's the only drawback inside a linked list. So all of these data structures, they are basically balancing of trade-offs. They give you some advantage and then they take away some advantage from you. So here the arrays, for example, you have some array. Okay, this array is called, let's say, nums, and it has numbers in it. Right? So this address is fixed, right? The size of the array items are fixed. So let's say each is n byte. Let's say k bytes, I would say. So if I ask you the array of m, then it's a constant operation. Whatever the address is, plus m multiplied by k. That's where the uh, m block will be located. But in the linked list, finding the index m would be considerably hard because you have to start with head. Not considerably hard, it's just linear operation. So start with this, and then you do a current dot next, then you do current dot next. You keep repeating this loop till you find m times, till your counter expires to m times, and that way you will reach the end. So in this array, searching an index is O1, but searching an index in a linked list is O of n, where n is the index. In that way, you have to do n operations to get to that index. Many times what happens is, I'll just tell you a trick beforehand and then we'll talk about it later. Many times we deal with the items itself and not the index. So this is a very common pattern that gets asked as well, and plus it's also good to know. Suppose you have a linked list, okay, that contains some items. So you have a head that is referencing, let's say, ABC, and then you have a next which is going to XYZ. Then you have a next which is going to PQR. Then you have a next which is going to DEF, something like that. And then let's say at this point the list ends. You can think of it as like 1,000 items. So if I ask you to add an item after, let's say, item XYZ, okay, add a new item after XYZ, and this item is 123, suppose. Then essentially what you'll have to do is you'll have to move head. You will have to start with the head, and then you'll have to go all the way to the list till you find the item XYZ. This type of searching operation can be enhanced. When you're searching by the item, can be that searching operation can be enhanced by using another data structure in conjunction with a linked list, and that item can be a dictionary or a hash map. I will just use a general term, hash map, where in the hash map you can store the items and their memory address. Whatever, let's say ABC and then DEF, PQR, whatever. So if I ask you to give me add an item after XYZ, then I can just, instead of traversing this list, I can just go to this XYZ, look for the key, look for the address M1, okay? Then I just directly reach this node in one operation. And then I can manipulate the items after that. I can add a new node, which is 1, 2, 3, and I can shift the references. I can just first delete this reference. Add this and add this. And then I can just enter one more and put M5 here. So all I need to do is add another data structure like hash maps to increase the searching of an item. Now, when I do that, I'll have an overhead of maintaining this as well. So if I, let's say, if I later on delete the node DEF, then I need to delete it from this as well. That's the overhead of this. And the another overhead is the extra space. So if the linked list is of size n, then the hash map will also be of size n. So you have 2n space instead of n space. But it increases the searching by constant time. So it makes the searching, constant time instead of linear time in that way, which is a huge gain in terms of implementation. So I am